Hello, thank you very much for coming. And I want to talk in this presentation about some challenges or some common pitfalls which some companies can meet in a way of building observability pipelines, what it is, how it differs from old good monitoring, and why sometimes some approaches is not work well. And about me, I am more than 90 years in industry, starting as a simple developer, working in different fields from low-level microcontrollers up to some high-level declarative languages, and worked in fintech and data science. And I solved and automated some problems in operation in the scale. And also I have some hobbies related with the music and theater, some projects which we made in cooperation with musicians in our country. So there is a quite common question: what is why observability? So do we like to DevOpsify monitoring, or maybe it's some sort of hype, some sort of new term which we don't need? And I want to cover such kind of things. The main overall problem in, for example, large enterprises where we have a lot of agile teams which can be distributed all over the world or distributed between different cities, is that it have very little control over that, because again we have teams that work independently, who decide to choose the technical stack and better technology for solving their problem. Or in case of large enterprises, there is such things as merchant acquisition, where a company can buy other companies with with another technology stack which should be integrated in a so-called global platform. For a small enterprise, for a small company, startup, there is another problem: how to find the best solution. And a lot of companies have failed on this way, and a lot of anti-patterns were developed. So, for example, you can see here some example of so-called distributed team who can be located in different cities, who can have some sort of product which covered with some sort of monitoring, some Zabbix, Sensu, etc. Somebody cannot have anything. And again, everyone has some sort of solution, and it is hard to get overall picture of operation in that case. And especially it's hard to orchestrate changes, again, because if you are too independent, you have less possibilities to manage all these things. So yeah, quite often Lozu can look like this, so everything is different, everything is coming from different places. And common anti-patterns, if we talk about collecting information about our system behavior, and I want to start to talk about metrics, is it's tempting to collect everything just in case, because probably we can need this kind of information later, and it leads to this situation that amount of metrics in monitoring grows exponentially. And at the end of the day, nobody understands what's going on in our system. And engineering complexity grows as well, because I saw in some companies that monitoring solution is more complex than a main business. For example, Uber case. You can see this information is taken from their engineering blog. They have 9 billion metrics. They have more than 1,000 instances for monitoring. They have 9 billion unique metrics IDs, so quite large numbers. But again, if you need 9 billion of metrics, you're probably wrong, because if we talk about the metrics, it's a low level resolution of behavior of our system. Trying to build metric as a logs is not a good idea, because those huge amount of metrics leads to unusable dashboard. So imagine you want to put all this huge amount of data on some dashboard, so no one can observe 9 billion metrics. And quite often it looks like spaghetti. For example, GitLab has a good example. So GitLab is a company which is famous for its transparency. So they opened all their operations dashboard to a wide audience. So this is just a small part, because there is another part of dashboards, and this is just this small piece of it. So you can multiply all these dashboards on this amount. So how can you get a picture what's going on in GitLab? So sometimes it's monitoring is just if you talk about some observation, it looks like you are watching some sort of spaghetti, and it's better to watch YouTube in that case. So there is like a question whether dashboards are useless or not. And actually dashboards are very useful, because our brain system is oriented on recognizing visual patterns. So we can catch pretty quickly some sort of visual data, but only in that case when you know where and when to watch. There is another approach when we work with a system such as Splunk or Elastic or Honeycomb. You need to have to create some queries to get your data. But querying requires some cognitive effort, because you need to create query, you need to somehow understand what you want to get, and again, it's not so fast in case when you're facing some incidents. So again, metrics is a low resolution of system dynamics, and they should not replace logs. So it means that it's not necessary to have millions of them. And why it's all about? We have operation teams. We have our monitoring or observability solution built on top of our production system, because we want to understand if something is going wrong. And incidents is something that have impact on your business operation. They're expensive, because, for example, some of incidents can cost some millions of dollars. In our case, company average cost is around 100,000 up to 400,000 1 hour. But more important, incidents come with a credibility loss from your customer. So here is this quite good query survey, where is estimated cost of an hour of downtime from last year. And you can see that a lot of companies fall in this area, and our company as well. But again, there is edge cases where the impact can be disastrousness. For example, you probably have heard about company who lose all their capital, about 400 millions within 40 minutes after they deployed a dead code. And this is quite famous story how a large company, investment company, get bankrupt after 40 minutes. So if you talk about the outages, then usually it's change, because even if you have a bug, you need to deploy this back into your system. Some sort of network failure, because again, network is quite unreliable. Bug, human factor, we all we are human beings, we make mistakes, hardware failure, and some sort of unspecified, but again, it's not so often. And let's see outage in dynamics. So we can see that any outage or incident has own timeline, and fixing is usually take a quite small part. It's quite interesting when you read post-mortem from the public companies. You can see that a lot of time is going to detect or understand what's going on, investigate, escalate, and then fix. So what is all about if we talk about the creating system about observability? So any reduction of incident or outage timeline will result in significant positive financial impact and moreover in credibility. And your operation teams will feel less pain, will feel less toil in their day-to-day work. So let's focus on KPI metrics. KPI metrics, why? Because it's almost impossible to operate on billions of metrics, as I said, and in case of normal behavior, there will be always some outliers in real production. And therefore, not all outliers should be treated as an anomalous incident. And here, quite good anti-pattern case is a Etsy case, Kale project. Etsy is a company, marketplace for handcrafted goods, which is with a headquarters in New York, and they're famous with their StatsD format, and they have a Kale project. Kale project collect metrics from 200,000. It was more than 200,000 metrics from the production servers from Etsy, and they tried using some sophisticated machine learning algorithm to find real outages, and that failed because if you have a 200,000 metrics, you will have outliers with every tick because due to statistical oscillations. And after struggling about 3 years with this project, they dropped it. And this slide is taken from the Andrew Clegg presentation, who is a data scientist in Etsy, and here's quite good lesson learned results which they take from the Kale project. So anomaly detection is more just some outlier detection, and one size fits all approach probably won't fit at all. There is no free lunches, there is no some universal way how to solve or detect problems on data, and not all anomalies should result in page alerts. The most important thing is just alert on anomalies in business and user metrics only. And the main paradigm shift came recently, because in our old days we run our system in a lump stack. We have a physical servers. We need to check, for example, CPU, disk usage, etc., etc. And the main paradigm shift came from the field of infrastructure, because we have right now clouds, microservices, orchestrating frameworks like Kubernetes, immutable infrastructure. So it changed how we build and operate our system. And all this give us abstraction from the hardware. So we have a abstraction from a hardware layer which provide for us computational resources. And moving towards abstraction of this hardware means that we need to focus on key performance indicators, which reflects how our business behave. And KPI monitoring, KPI metrics, it's related to the core business operation. For example, it could be logins, sign up, deposits, transfers, whatever. and usually they're heavily seasoned because any metric which is related to human being activity has a heavy seasonality because we are asleep in the night and active to the day. And for example, static thresholds won't help here. This picture, by the way, is taken from the commercial product Anadot, which costs like a small jet, and try to solve the problem of finding anomalies in such seasoned metric. But it has a lot of flaws as well. But we had in our company some terrible system, which called Hewlett-Packard Service Health Analyzer, which in the marketing prospect was like, I don't know, full of unicorns, machine learning, artificial intelligence, everything is learned by itself, so you just buy it and feel happy. In reality, it was a black box. Nobody understand how it worked. There wasn't a possibility to set up it in any way, so this is part of its horrible user interface. And we had a huge amount of false positive, which is quite bad because this is the same situation as a boy who's screaming the wolf a lot of time, and when the real wolf come, nobody believes it. Because it's very easy to set up alert or monitoring system in a very precise level, but after that, at the end of the day, we will start to fight with the huge amount of false positive. And in our case, another problem was that we get information about incidents where we already know that we have a problem. So it gave no any additional information for us. So I want to show some approaches working with time series data. And time series data is quite popular right now. So we can see that trends in a database engine, the time series databases is faster, like growing trend in the last 2 years. And for example, there is a lot of solutions like Timescale, InfluxDB, where it's possible to collect and store metric information. And let's see time series data. So actually, this is real production data. You can see this is heavily seasoned. We see like a Monday, usual work days, and we see a Friday where people have some fun, Saturday more fun, Sunday a bit less, and new week is coming. So how we can process, how we can analyze this data? So actually, all time series we can divide it on 2 types: stationary time series and non-stationary. So stationary is quite simple. It actually looks like white noise and can be described using 2 parameters like mean and variance. And it do not change these properties if we shift this data. Why? It's quite important to have some sort of test about stationarity of time series, and I will show you why. And other, for example, data, for example, with trend line is non-stationary, or we can have a dispersion change. And for example, let's try to create a model of our data. Let's start with just very simple thing called linear regression. We just cut half an hour data from our week, and we try to build a regression line. So regression line actually minimize the sum of square distances between line and the points. And it means that we can reduce the dimension of data from 30 points here just up to 2. So like slope and the starting point. What is all about? How we can prove that our data, that our model is actual, that this model is catching the signal. every measurement, as you can, for example, remember from the physics, consists of some signal plus some error. And if we have a model which we want to test, then we can subtract our model from actual data, and the more model fits to the signal, the more residual will be look like error, like a stationary time series. But how can we be sure? So there is a statistical test called Dickey-Fuller, which can test our time series data on a stationarity. For example, whether this time series is stationary or not. So this one, first one with the trend line, is rejected with a high probability that this is not stationary one. And you can see there is a autocorrelation quite high. But if we check our residual, we can see that result is totally different. So this residual is actually stationary time series with such kind of probability. And for example, if we go further, we can make a segment regression, so we can cut our data on such a pieces again and again. We can build all this regression line, put everything together. There is some small gaps between them, but this is okay. And again, if we subtract from actual data our model, we can see this is residual. There is even some outlier here, but our Dickey-Fuller test says that this is okay. This is stationary time series. It means that we can prove any model whether it catch the signal or not. And there is, for example, another approach using Harima models, but I want to show you effective one which we use in our systems, which you can use, for example, building a system which work in an automated way for finding some anomalies or finding some outliers. So again, this is our data, weak data, and let's apply moving average on that data. Moving average with a window means that we have, for example, some window, let's say 60 minutes, 60 point. We calculate average of this 60 point and put in the center. Then we shift our window on one point and repeat process. So at the end, we will get this kind of data which preserve all the trend lines but removes the noise. And actually moving average is working as a low pass filter which remove all the noise, which actually is represented as a erroneous factor in our measurements. The same way we can do with the moving variance. So we can build, for example, some boundaries for our data. And if we put the data from next week into our boundaries, we can see here that we have some sort of outliers. But as I said, the outliers, violations, is not the same as alert, because we as a human beings, if we see that something is going on, we try to figure out or check in another part of the system to collect more information. So actually we have a two part of a system. One is information emission, okay, when we find, for example, some outlier and send it out. And another one is information consumption, where we collect all the violation and try to correlate that. So here is a predictive alert system which I've built in a Playtech within 1.5 years, which found the anomalies on metrics and combine it with the rules. And rules are dynamic, so there is no like static values around them, but rules are applied to the model values in a specific point. This is how this system looks like, but again, it's quite complex, and you can read if you want into the articles in the Medium in the end. And here are some sort of rules we have, and it means that we have conditions where we can set up it without static thresholds. So for every type of metrics, it's possible to get specific model values and compare with them. And again, we also it's also important to calculate derivative to difference between points, because you can have a speed of falling, because the slowly decreasing metrics could be related to some business case, for example, some slower activity after 1st January or something, but the fast drop is more important, especially for large metrics. So here is the system which looks like we collect the statistical models, which we, for example, take for 4 weeks, and we have weights for every model, which result in combined model, and you can see how productional data is quite fit well. And this approach also gives a possibility to have a optimization, because again, actual data is always changing in time, and it's possible to use an optimization algorithm standard. You have a loss function, which is minimize square of distances from actual data from the mean, but you change only those weights, and algorithm says that the solution optimal always will be found. And usually in 95% of cases when you have regular metrics, it works perfectly. So we have such kind of things which, for example, can find and correlate different kind of metrics, and said that, okay guys, you have, for example, some problem on login service, some sort of activity, and maybe deposits, etc., etc. So I want to show some results what we have. So the red area, it's a most trouble one. This is customer detection. This is where you get information about your problem from your customer, and you can see that it was quite large for a long time. So the green one is a monitoring, which is automated monitoring solution. This downwards is a change deployments where all problems were related to that. And here is own observation. So as I said, the problem was to collect the information from the different teams, from the different data centers to some central storage. And after collecting information from different data centers to central storage, here we have some sort of central visibility. For example, using Prometheus, there is a project called Thanos, which also can combine or aggregate data from different local setups from Prometheus into one. And after that, you can see that, okay, own observation increased. It means that it was stupid work, it was toil, where operation guys just sitting and watching dashboards. Absolutely stupid work with a huge possibility of mistakes. And here we pushed into production system which built on top of machine learning, which starts to monitor critical components. And you can see that right now we have a customer detection dropped to some percents. We have a large, very large part which is detected by monitoring and some sort of own observation. But what is all about? If we talk about observability, there is a so-called different pillars, as they called. We have a metrics which represent the low-level resolution. We have a traces which can bring information with the details about system behaviors and, for example, have log aggregation. For some companies, log aggregation is not feasible because, again, if we have let's say 72 data centers which generate a huge amount of logs, then attempt to collect everything in some central place will cost so much resources and traffic and storage and so on, that this is just from the economical point is not reasonable. So some companies do not aggregate the logs. They have logs which is local to their clusters or data centers. And if we talk about the general view, then we are looking for anomalies in our metrics, that something is going wrong. But on a higher level, we need to find some regularities. For example, if one metric is falling or increasing, or another one falling again, so we can correlate all this stuff. And another important thing is combine events from organization. It could be deployment events, deployment started, deployment ended. It could be automation test results. It could be, let's say, a marketing campaign. So it's possible in automated way correlate all the anomalies, which again could not be an incident, but it could be combined and bring information with the context that this relates to the deploy, this increase is related with the marketing campaign, and it means that it also brings the out-of-the-box business information. And in that case, you need a time series storage. Why? Because from the most important things, we haven't predicted delay on network. Because again, network failure is quite often, especially if you operate with some Asia sites and from USA, and it means operating worldwide is a problem. And cap theorem means, cap theorem is that you can choose consistent or availability, but in case of dynamic system, it means that you can receive signals from the past. Imagine that you have signals coming from different data centers, which should trigger some alert. And one signal from data center is missing due to a network failure, and the condition didn't met, alert didn't come. But after 2 minutes, connection is restored, and event is finally come. It means that it comes from the past. It means that if we have some complex event processing in a window, we need to check not only the past, but the future as well. So again, how long this window should be in the future. Another part, which is quite important, is that if we took the same as the logs, if we collect some events or metrics, then 90% of them are boring. We only need them on demand. We do not need to process everything. We do not need to process all the stuff we get. So again, a lot of things we need only on demand. So combining all together, for example, metrics with the traces and event can reduce investigating part, because with the metrics you can very fast detect some problems, but metrics do not tell you anything about the what's going on about the investigation part, and tracing in that case is what you need. So tracing is a so-called higher resolution of your system dynamics versus metrics low one, and distributed tracing can reveal unknowns, because if we collect some metrics, we usually want to cover some things that we want to know, and it reduces the investigation part of incident pipeline. And here I'm just show quickly some real production case built on top of Jagger, open source open source solution by Uber, which is quite easy to set up, quite easy to test, and quite easy to cover some critical part. And Influx version 2.0 supports the backend storage, and it's quite important when you have all the events, all the signals in one place. So here is Jagger as a backend storage, and Influx 2.0 as a backend storage, real prod case. And we received approximately 8,000 traces every minute. And we had a performance issue with limitation of I/O connections. And there were a burst of context switches, which leads to increasing this part of computation. So this is a piece of work which takes a query to the database, which was quite constant, network hop, results, and back. And here is the computational part, which work quite memory and CPU intensive, but in normal case it's take 3 milliseconds. Here it was up to 40, 50. And this is just the impact of context switches, which flushes the caches, TLB buffers, and etc., etc. And the root cause was the default Postgres settings, which were created for hard drive and were very so-called limited. And this problem were hard to catch, to find using only logs, because you need to compare a lot of like timestamps and a lot of other things. So again, finding anomalies on a lower level, tracing, collecting event logs, finding irregularities between them, and building topology on top of that, and we can call it IO apps. And I want to make a quick intro into InfluxDB, because this is one of the leading time series platform right now, which gives a lot of possibilities to building observability platforms, and it has a good isolation. It can be a central storage for metrics, events, and traces. It has a streaming paradigm, so you can define transforming of your data in a declarative way, and I will show some examples. So again, if you can process, if you can bring processing the data closer to the data storage, it's a win, because you don't need to receive chunks of data to the application where it's processing, but it's easy to have some tests, to test hypotheses, and combine all different kind of information. So here is a real incident. This is an activity which came down, real incident, and we need some statistical model to operate, for example, on this data. We need statistical model to understand is this significant fall or not. And the same metrics taken from the login part. So again, we also can see that logins are also decreasing. Again, we need a statistical model to model that. But let's take the correlation out. Let's just have the check the relation between them, and relation dividing mostly take a lot of correlation out, so we can see quite much or less stable time series. And again, we can see our incident here. It's easier to model, but what is all about? There is a quite famous concept, random walk, where processes which has a lot of random factors could be easily modeled as a next point is equal previous one plus some erroneous component, which means that the erroneous component could be found with subtracting current and previous point. And this kind of stationary time series is very easy to model, because again, this error factor is stationary time series. We can describe it only using two parameters, mean and variance. and we don't need to have a statistical models. We can have just some reservoir for that. So this is our the same data, same incident, where we take the error factor, or again, this is discrete derivative because we make a difference between points, and if we have a similar interval, then this is discrete derivative, which is described in a Flux language in Influx, and we can actually can check the changes of main parameters. So in our case, this is variance, or I can make it more like visible. So you can see we don't need to have a huge statistical models. We can store some sort of reservoir where we online collect some data, how it's changed, and if we see that the changes of the data is variance is rapidly changed, there's something going on. Because if we have large processes with a lot of random factors, then we have a lot of randomness in our calculated series. Another one is a security case, which is, for example, we have a successful and failed logins. But again, statistical models will not work here very good, because again, in the case of increased activity, people make some typos, and you will face increased failure login count. So simple threshold will not working here. So here is again using some simple transformation of relation between failed and successful login. We can see quite easy some real attacks on our login services. So this is a real alert which were catched by our internal system, and again, this is quite easy to separate normal flows, even in the case of changing statistics and activity from the normal one, and using with the metrics, with the traces, with the events, common metadata, for example, is this related to some service, is this related to some data center, etc., etc. It's possible to build a topology on top of that. And topology, which uses the common semantics, can bring inference. For example, if we have some problems in some parts, we can quickly understand or give information with the context. Guys, we have a problem here, and this is related to some critical services or some critical things, so probably you should check it next. And a lot of commercial solution, for example, some Datadog, Anadot, Uber internal system, they also have the graph models as well. And even my home, so I'm here, but I have some sort of control over my home, some temperature, some light condition, etc., using the same approach. So I can set up a system for monitoring that. And due to the success of our internal system, we had a really huge success in the company, because we have more than several millions which were preserved due to the early detection, due to the fast reaction. And the more we have a huge credibility increase from customers, because right now customers get information about their problem from us, not vice versa. And we decided to build rewrite an engine and make it open source, because again, we have right now open source time series engines, timescale, Victoria metrics, InfluxDB. We have a good tools for visualization, Grafana, but there is no general so-called engine for processing metrics, for processing traces, and we decided, to create this kind of engine. A lot of people from different companies involved in that, and we think to put it into GitHub within some couple of months. And core engine written in Java, reactive drivers, a lot of different guys who helped us in that way. And usually, when you plan to have something, you have a like a plan that everything will be like fun and strict. But we are also something right here. But it is a fun way, which I'm very like to go through. And here is my Twitter. Here is my Medium blog, where I have a lot of different articles related to those topics, to the observability, to the system we built, to the approaches, to the comparing logs versus events, etc., etc., and a lot of some just Twitter postings as well. Thank you.